Yes, we made it to the free response questions. There's going to be 4 of them on the AP exam, and usually each problem has like 5 or 6 parts to it, and this is not going to be any different. You'll have problems on trigonometry, data modeling, calculator problems, non-calculator problems. This is problem 1. This is a calculator problem, and this is data modeling, so this is 6 parts, I believe. Let's just jump right into it. Consider the function h of x as depicted in the provided table. So there you go, with a domain consisting of the values 1 and 2 and 3 and 4 and 5. Additionally, we are presented with another function, j of x, defined by j of x equals 5 log of x. So we'll probably need our calculator for a lot of these. Define the function k as k of x is j of h of x equals j of h of x. Determine the value of k of 4 as a decimal approximation or specify if it's undefined. When would it be undefined? Like if x is negative or something like that. So let's see what we need. We have k of 4 they want. Okay, and again, this is part I, part 1, part I. K of 4, I'm going to use this version of it, equals j of h of 1, and let's get different colors because I can. So let's see what we have. H of 1 is found by taking the 1 in this guy and saying, oh, well, 1 maps out to 7, so h of 1 is 7. So this becomes j of 7. Now, how do we find j of 7? We're going to need our calculator for this one. So j of 7 is going to be 5 log of 7. Now, by the way, just in case I haven't said it or you haven't noticed it, this is invisible base 10. So yeah, you could pretty easily plug this into your calculator, and that's what we're going to do right now. All right, 5 log 7. Again, the log that we saw in the problem is the same log that we see here, invisible base 10. Going to get a pretty terrible number, 4.2254, so 4.225. Remember, when we do these, we round to 3 decimal places. So 4.225. Let's go back and write that out. All right, so k of 4 is going to be roughly 4.225. So that's it. That's all we have to do. Now, again, I know I said it in the calculator thing. Since this is an open-ended, we have to make sure that we round to 3 decimal places. So this is our approximation rounded to 3 decimal places. So that is part I. Now, part II, or E for Joel Embiid, because he has 2 I's in his name, Philly fans? Determine all values of x for which h of x equals 7, or specify if no such values exist. Now, the h is this guy. So, what x values give us h of x equals 7? Well, there's 2 of them. Now, this is not saying, hey, let's plug in 7. No, this is saying this is h of x equals 7 right here. So your 7 and your 7. So what x values seem to do that? 1 and 5. So x is going to equal 1 and 5 for this guy right here. Okay, so no calculator. This one was one of the simpler ones, so I'll definitely take it. Okay, problems 1 and 2 of part A complete. Now let's take a look at problems 1 and 2 of B. Consider the function h, it's the same thing, I don't know why I'm reading it. Discover all the values of x as decimal approximations for which j of x equals negative 7.5, or indicate if no such values exist. So this is me taking the j guy and replacing j of x with negative 7.5. So negative 7.5 equals 5 log of x. So what I need to do is solve for x here. Well, x is trapped inside of a log. All right, x is trapped inside of a log, so what I have to do is I need to get log all by itself so I can get x all by itself. So if I divide both sides by 5, that gets the log all by itself. Okay, so this is actually -3/2. Now, if you didn't know that, this is a calculator section. By all means, use a calculator. You can write that out as negative um, 1.5, but I'm just going to keep on going. That's going to equal log of x. Now, again, log of x means invisible base 10. If I want to get x all by itself, I can take the 10 to the of both sides. Bad grammar? Absolutely. You could just write this out in exponential form, but I prefer doing it this way. So x is going to equal whatever 1 over 10 to the 3 halves is. But what it is it's not going to be a pretty number. At least I don't think it is. I mean, no, it's not going to be a pretty number. I'll just stop right there. So let's run to our calculator and find out what 10 to the -3/2 is. So 10 to the -3/2. The nice thing about these guys is it actually gives you 10 to the right in front of log, or right with log. I wonder why. -3 divided by 2 is going to give us 0.0316. So 3 decimal places is 0.31 or 32. 0.032. I don't know if I said that correctly, but that's what we're going to write out. 0.032, that's going to be our guy. 0.032. And if you're wondering why is it so ugly, well, when you have a number taken to a negative exponent and that negative exponent is greater than 1, it's just not going to be the prettiest thing ever. This is asking you 1 over 10 cubed, but then take the square root of 10 cubed. So 1 over the square root of 1,000, big number. Okay, so 1 over a big number is going to give you a small number in the end. Now here's where we have to just double check things. Can I take this, since this was j of x, plug that in, can I take 5 log of 0. Blah, blah, blah? Yes, I can take the log of any positive number as long as it's not 0, as long as it's not negative. This is awfully close to 0, but it's not 0, so this will work just fine. Okay, so yep, this is allowed. Values do exist. I get one answer, and that's my one answer only. Now it's 2. Ascertain, that's a word you don't see often. The end behavior of j of x as x increases without bound. Express your answer using the mathematical notation of a limit. Now, if you need to graph this out, go ahead, be my guest, graph this out. Go to y equals 5 log x. The reality is this is nothing fancy at all. This is a log function multiplied by a positive number, which means it's just going to be a warped version of a log function. Log functions look like this. Okay, everything, remember what I said a second ago, you're not allowed to have negatives, you're not allowed to have zeros. So a log is going to hover awfully close to the y-axis and then go like that. It will never at any point touch the y-axis. It'll never cross the y-axis. It's always going to stay to the right side. Okay, so the end behavior of one of them is going to be obvious. As we move to the right, as we increase without bound, this is going to continue going up and to the right. So the right side, okay, the limit as we keep moving to the right, the limit as x approaches infinity of j of x is going to also be infinity. Okay, if you're wondering, well, won't that flatten out somewhere? No, it will never flatten out. Now, what's going to happen is, yes, this will continue to get flatter, but it'll still keep going up and to the right. It'll never at any point stop going up and to the right. Okay, it'll really do it slowly, but this will continue going up and to the right, meaning that it'll be infinity. Now, if you're thinking, all right, the limit as x approaches negative infinity, you're wrong. See, we can't go to negative infinity. We can't. I mean, we keep going left, and we hit this roadblock right here at the y-axis. So the y-axis, we can't go any further than that. In fact, since the y-axis represents an x value of 0, we can't even hit the x-axis. But what we can do is we can approach that 0 from the right without actually touching it. So we're going to say the limit as x approaches 0 from the right of j of x. Now, as we approach 0 from the right, we're going down, 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 down forever. Okay, and this kind of is obvious here as we have a small x, we're hitting negative numbers. So this is going to be negative infinity. Okay? So that's the end limit of a logarithmic function. Remember, the end limit of logarithmic functions are never going to be limit as it approaches infinity and as it approaches negative infinity. You're going to have to hit a roadblock somewhere, and that's what we did with this guy. All right, so part B, dendo. Let's do part C. Consider, I keep doing that. Determine if H possesses an inverse function. All right, I'm going to tell you this and tell you this right now. When I was looking at the practice examples of these, you are not allowed to say it fails the horizontal line test. Now, if you're like, whoa, what's a horizontal line test? If I were to graph these points, right, I get 1, 7, 2, 4, 3, 1, 4, 4, and 5, 7. Okay, now you know what the vertical line test is. The vertical line is you draw a vertical line, you pass it through your function, and if your vertical line hits a spot more than once, it's not a function. So if we were to flip this sideways, which it would be, like the inverse of this would be dots going like this, okay, because you would just flip the functions. I'm sure we're going to do that at some point. If you're thinking, oh, well then, if we were just to make believe that this is going to turn into this, why wouldn't the horizontal line test hitting two dots not be good enough? I don't know. But for whatever reason, you're not allowed to say it's invertible because it fails the horizontal line test. You're not allowed to say that. So what we will say is we will say something like this. Okay? We have the 5 points of H inverse of X will be, and I'll just take these and I'll flip them around. So it's 1, 7, 2, 4, 3, 1. In order to find the inverse, you literally swap the X's and your Y's. So our 5 coordinates will be 7, 1. Maybe I should say coordinates instead of points, but there's nothing wrong with saying points. It just sounds more professional, I guess. 1, 3, 4, 4. And 7, 5. Since an x value of 7, I'll just say since an x equals 7 is not 1 to 1, H inverse of X is invertible, or is not invertible. Okay, so again, it's not good enough to say, I did the horizontal line test and the horizontal line test failed. You have to explain what it means for the horizontal line test to fail. 7 maps to 2 different numbers after I flip them. 7 maps to 1 and 7 maps to 5. A function cannot map to 2 different y values. Therefore, H inverse is not a function, which means it's not invertible. I don't like it. I don't like that the people decided that, yeah, not good enough, friend. Don't like it. But that's what they decided, and I can't help it. I don't make these tests. Now, I make this test, but I can't make these tests. So something to look out for. Provide rational, you're kidding me. So all I had to do for 1 was just say, no. That's really annoying. So let's try this again. And this is a good learning experience because by drawing a rough draft, it allows me to maybe write this a little bit better. So I'm okay with this. Determine if H possesses an inverse function. It doesn't. Okay. End sentence. Now, what does that provide a rationale for your response to this one? All right, let's word this better. 5 points, or 5, I didn't like the word points last time, so I'll change it to 5 coordinates of H inverse of X are, and I'll write it out as again, 7, 1, 4, 2, 1, 3, 4, 4, and 7.5. Now, I want to expand a little bit on what I said. The point or the x value of 7 maps to both 1 and, what's the other one? 5. Therefore, H inverse is not a function because it is not 1 to 1. Okay, this one's 1 to 2. And you could have used the 4s if you wanted to as well, but I like this explanation a little bit better. So a blessing in disguise. And also, as I started to write this out, I realized I was running out of room and I kind of wanted to rush my description. So I'm happy with this. But this is an example of what a problem could look like. You have some modeling, you have some inverse stuff, you have some other stuff, some calculator stuff that we had to deal with. Not all calculator, just a little bit. But, you know, something to expect. All right, so that's problem 1. Hope this helps. Welcome to free response question numero dos, or FRQ2, as the kids on the street say. No one says that. This is a problem where a calculator is allowed, and we're just going to get right to it. Imagine a biologist conducting research on a particular species of bacteria in a laboratory setting. So close your eyes and imagine that. In 2018, where T is 5, time is 5, the biologist observes 200 bacteria. By 2024, this year, where T is 11, the population had grown to 800 bacteria. The population of this bacteria species can be described by the function B given by, an exponential function, where B of T represents the number of bacteria in year T. Usually when you're dealing with some type of growth or a population growth, it is going to be exponential, and so that should not come as a shock here in any way whatsoever. So, A and B are just some numbers we need to figure out. B of T is the total population after T amount of time. So use the given data to create 2 equations for finding the constants A and B in the expression B of T. So what part A I is asking for is come up with 2 equations, like a system of equations. Well, in order for me to come up with the equations, I have to take some of this information that I have right here. So what I do have is that when T is 5, I have a population of 200. So that gives me the coordinate 5, 200. So using that information where 5 represents T and 200 represents B of T, I can come up with the equation. Instead of B of T equals AB to the T, I can come up with the equation where I substitute B of T with 200. A is I don't know, B is I don't know, and T can be 5. So that's one equation. Now, if you're like, oh, I think I know what's going to happen next, you're probably right. We have another coordinate that's 11 and matches up with 800. So I have 11, 800, and that gives me the equation, replace B of T with 800, A is I don't know, B is I don't know, and replace T with 11. So what we have here is a system of equations, and I can use that system of equations to help me solve for A or B, which is something that I absolutely don't want to do in this situation, but I could if I really wanted to. Now, what I'm going to do instead, since this is a calculator problem, I'm allowed to use my calculator. I'm going to do 2 by using exponential regression. Now, exponential regression is something that you could do in your calculator that gives you something in the form A times B to the T. So I can run to my calculator, I can type all this information in, it's going to spit out some probably gross numbers, but I'll be all right, and then we'll write that down once we're done. Be right back. So exponential is going to start out just like any regular regression problem. So we go to Stat, Edit, and we type in our points. We had 5 matching up with 200. We had 8 matching up with, 11 matching up with 800. Got those backwards. Could have been dangerous. Now, what we do when we're done with our 2 points, and that's all we have, is we go to Stat, Calc, all the way down, I think, to 0 is exponential regression. Yep. So 0 is exponential regression. Now, since I'm going back and forth from my notes to a calculator, I'm not going to store this regression equation because it won't work for me. It'll disappear by the time I go back the way that I'm recording this video. So I'm going to ignore that. I'm going to hit calculate, and it gives me something awfully gross. Unfortunately, it's not 63, it's 62.996 and 1.2599, so 1.260 is going to be my guy. So I'm going to go back and use that information right there to come up with my equation. All right, so we ended up with y equals blah, blah, blah to the x. Well, I'm not going to write out y equals. I'm going to write out b of t equals, it was 62.996 times 1.260 to the t power. Now, I could have come up with those numbers using this method, but you could see why I wouldn't want to use substitution or elimination or whatever god-awful mess it would be. Log would be involved probably. I don't want to deal with that, so I'm not going to deal with that. Okay? All right. Part 2. Same question. Utilize the provided data to determine the average rate of change of the number of bacteria measured in bacteria per year from 5 to 11 years. Well, fortunately, we're given 5 to 11 years, so that makes life easier. Express your answer as a decimal approximation and show the computations that lead to your answer. Normally, when you think average rate of change, you think f of b minus f of a over b minus a, right? Well, the same thing's going to happen here, except I'm going to use b's and t's. But I'm still going to use little b's and little a's. So this is the part that counts. That blue part doesn't count. I'm going to write out b of b minus capital B of a over b minus a. Okay, now I know what these are. These are going to be my B and my A, so you're going to be 5 and 11, but let's do 11 minus 5 in that order. Let's do 11 minus 5. I don't know why I would put it the other way. No. Yay. B of 11, I'll deal with in a second, minus B of 5. Now we know what those are. B of 11 was 800. Minus b of 5, we know is 200 over 6. So you become 600 over 6, which becomes 100. So this is going to be measured in bacteria per year. It's going to be an increase of 100 bacteria per year. Now, that's just the average rate of change. We already know very well from the previous problem that this is an exponential guy, so it's probably going to look something like that, but this is asking you to find what that is right there. Find the slope, and the slope is 100 bacteria per year. So, interesting problem. Use the average rate of change found in 1, which is 100, to estimate the number of bacteria for t equals 14 years. Show the work that leads to your answer. Well, we have 11 years, and 11 years is 800. So the work that I'm going to show is the fact that 14 is 3 more years more than 11, more, and I'm going to multiply that by 100. That's going to end up being 1,100 bacteria. So I didn't show a ton of work. I'm not sure what other, unless you want to describe or explain what's going on and say, I am adding 3 because that's 3 years after 2000, whatever. I'm always very paranoid where I like to show or write more than necessary. I don't know if they'd accept something like this. Maybe they would. I'm sure they would. But if you're always paranoid, just add more. Just make sure you don't make a mistake. The average rate of change found in I can be utilized to estimate the number of bacteria during year T for T is greater than 15 years. Will these estimates obtained using the average rate of change be less than or greater than the number of bacteria predicted by the model B during the year T? So, okay. Oh, and I only care about 15 to 25 years, not including 15. All right, so this is what I have to do. I have to compare what I got in part 2 of part A on the previous slide. And if you remember, that exponential function was not y, b of t equals 62.996 times 1.260 to the t. That's my exponential guy. Now, my linear guy can be found by saying, all right, well, my slope is 100. So y equals 100x. I don't know what my y-intercept is, but if I take one of these points up here, like the point that I just came up with, what was that? 1010. If I take a point like that and plug it in, I get 1010 equals 100 times 14 plus b. You become 100,000 or 1010 equals 1400 minus 1400 minus 1400. B is equal to negative 300. So the linear equation that I get that is supposed to do a good job predicting data after 15 years is going to be y equals 100x minus 300. So what I need to do is I need to graph u and I need to graph u on the same graph. What I want to do is I want to compare what's going on between 15 and 25 and see which one, or see if the average rate of change, see if the linear one is less than or greater than. So again, I'm going to get a picture like this, right? And I don't know what my line is going to look like, but I need to find out, is my line greater than the exponential guy or is my line less than the exponential guy? And that'll be my answer to that. So let's run back to our calculator and figure that out. Okay, so let's graph them both. Like I said before, it sure would have been nice if I stored the exponential function, but since I'm going back and forth to my thing in the calculator, it deletes everything automatically. If you were able to store it, good. It would look like this, 62.996. And of course, if you did store it, it's going to give you a whole lot more points, but oh well. Times 1.260 to the t, so to the x. That's my exponential function. It's going to show up in blue. My y function is going to be y equals, or not my y, my linear is 100x minus 300. If I hit graph, I'm not near at all where I want to be. Okay, now what I care about, first off, is a window between 15 and 25. First, I need to see where these intersect. So I'm going to zoom out until I can see where they intersect. Not yet. Zoom out again to see where they intersect. That might do it. Okay, now it intersects like way up here. So what I'm going to do is I'm going to set my window to 15 to 25 because that's what I care about for my x values. And why don't we change my y min to 50 and just see what happens. Well, that's unfortunate. Let's zoom out again. Enter. Okay. So let's change my window to, let's do 100. Let's change this again from 15 to 25. And that's again unfortunate. So let's zoom out one more time because I'm trying to get the y's. All right. So what is this? What is this x value? Oh, the x value, hold on. The y value, okay, so the intersection here happens at 196. Okay, so let me see. Where does it, okay, okay. Let's do this. Let's go up to 500. I think I got it. Let's go up to 500. And by the way, this is kind of like a good thing that this is happening, that I'm like testing stuff out. If you're like zoom fit, that might be useful, but it's too late. Let's change this one last time, hopefully, please, Lord, to 15 to 25. Hit graph. And how is this still not working? Am I still too low? What if I made this 1,500? Just overdo it. Hey! So now I don't see my exponential function. So let's make this 1,000 to 2,500. So much troubleshooting. Ah! All right. So there's my linear equation. There's my exponential equation. You can tell by the colors, but this is between 15 and 25. My linear equation is underneath my exponential equation between 15 and 25, no matter what. So it took all of that for us to figure out that our average rate of change possibility is going to be less than the model that we predicted back in part A. So after all of that, that's our answer. So let's go back and do that. All right, so after all of that, if you gave up on the video, I don't blame you. But what we saw is this guy, where the linear graph is below the exponential graph. So the average rate of change is less. The average rate of change, that's two ofs. The average rate of change will be less than. And to explain why, ... we'll write it out over here, because the graph of our average rate of change formula is below the B of t formula. So not a lot of room to write all this stuff out, but I was able to make it work. Sloppy, but I was able to make it work. So let's close this puppy out. Imagine, same problem. For which t value, t equals 8 or t equals 20, should the biologist have more confidence when using the model of B? Give a reason. All right, well, the model that we have is a model based off of numbers between 5 and 11. So it's going to be clear that t equals 8, okay, would be a better prediction because 8 lies in between our given t values of t equals 5 and t equals 11. Since t equals 20 is much greater than t equals 11 was the biggest one, our model may not show as much accuracy. Which makes sense. If you're going to predict something between 5 and 11, or predict something based off of 5 and 11, 8's literally right in the middle of it. 8's in the middle. So you wouldn't say, oh yeah, I'm more likely to guess what's going to happen for 20 than for 8, because you could graph these two and you can at least estimate what's going to happen in between. It's hard to estimate what's going to happen at t equals 20 because 20 is way down the road. So we did it. We did free response question number 2. Lots to do in this, lots to handle, but hey, I'm happy for us. I'm proud of you. So, as always, I hope this helps. All right, free response question number 3, the traditional trig looking problem. I've seen a bunch of practice problems that have this picture and involve some type of oscillating figure, like whether it's a Ferris wheel spinning around or a bike pedal spinning around or a metronome going back and forth. In this case, we have a pendulum desk decoration that uses a magnet to keep the weight hanging at the bottom of a string swinging back and forth in all directions. So this was pretty popular when I was a kid way back when. You would get these things that you put a battery in and this thing hangs from the bottom and there's whatever the battery does creates some kind of electromagnetic field where this guy goes back and forth and back and forth and back and forth. So you can kind of assume, all right, well, the back and forth, the back and forth, the back and forth, that's where the waves come from. The weight reaches a maximum height of 3 inches off the desk and a minimum height of 1 inch off the desk. The pendulum sways back and forth, completing 3/4 of a cycle per second. The sinusoidal function h of t can be employed to model the height h with respect to time t. The pendulum weight is at its maximum height at t equals 0 seconds. Okay, so pretty much what we're dealing with is no calculator allowed. All right, if I were to, I'm not even going to draw a sinusoidal function. Draw the picture out. Usually I draw the picture out, but that seems to be done for me. Actually, you know what? The heck, I'm going to do it anyway. Let's take the information that we have and make ourselves a rough draft. Now, obviously, real life stuff, so all in quadrant 1. At the very top, we're at 3. At the very bottom, we're at 1, which puts us at a midline of 2. So right now we could start saying you would be my 3 and you would be my 2 and you would be my 1. Okay. The weight reaches maximum height of 3 and 1 inch off the desk. The pendulum sways back and forth complaining. I'll get there in a second. The sinusoidal function h of t can be okay. So it's at the maximum height at t equals 0 seconds. So it's already up here. Okay, which screams cosine, and this is going to go down and come back up. Okay, now it completes a cycle every 3/4 of a second, which means that's my period right there. Okay, my period is 3/4. Now, I don't know if I'm going to need this. Maybe I will, maybe I won't, but this is what I have already. Okay, I have this already. So the graph displays h and its dashed line midline for 2 complete cycles. Points A, B, C, D, and E are marked on the graph. No scalar axes are provided. Determine the potential coordinates t, h of t for these 5 points A, B, C, D, and E. All right, so right off the bat, we could do A as our maximum. So we could say that A is 0, 3. Okay. So you would be, this is where it gets a little complicated. So 0, 3, that part's pretty easy. B is going to be something 2. I'll get there in a minute. C is going to be something 1. I'll get there in a minute. D is going to be something 2. I'll get there in a minute. And E is going to be 3/4, 3. So that gives me E. Okay. Now, if you're like, whoa, 3/4, where did that come from? It completes a cycle at 3/4, which means the period is 3/4. Did I say 3/4? 3/4. All right, now we're going to have to do a little bit of math. Okay. So everything is going to be based on the fact that we start at 0 and we end at 3/4. So it hits its minimum at half of 3/4. It hits the midline here at 1/4 of 3/4, and it hits the midline again at 3/4 of 3/4. So if you followed what I just did there, B is going to happen at 1/4 of 3/4. Okay, so whatever the distance, this goes from 0 to 3/4. This is going to be 1/4 of it. So 1/4 of 3/4 is 3/16. My favorite Bible verse. So this is going to happen at the x value of 3/16 and a y value, or in our case, t and h of t, of 2. So 3/16 and 2. Now I hit the bottom literally halfway in between 0 and 3/4. So C's x value or t value is going to be half of 3/4. Okay, 1 times 3 is 3, 2 times 4 is 8. So I've got 3/8 1. So C is going to be 3/8 1. Okay. This is going to be 3/4 of the way to 3/4. So D, the t value, is going to be 3/4 of 3/4. 3 times 3 is 9. 4 times 4 is 16. That gives me 9/16, 2. So D is 9/16, 2. Now, the reality is there's an infinite amount of answers here, right? Because if I wanted to be a silly goose and start at 3/4 3, I could have. But I didn't because I'm not insane. So that's why it says potential coordinates. All right, so that's A is coming up with 5 points. Hooray! B is going to ask us to find the function. Oh, and like I said, this screams cos because it is cos. Determine the values of the constants A, B, C, D. Blah, blah. So again, my rough draft, right, had me starting up here at 3, midline at 2, and bottoming out at, well, let me put the dash line here, bottoming out at 1. Okay, we went down, bottomed out, and repeated at 3/4. Now, if you don't remember what means what here, A stands for amplitude, okay? Now, the amplitude is half the distance from the top to the bottom, or it's the distance from the midline to the top. Okay, so the numbers are friendly enough where we could say, oh, okay, well, the amplitude is just 1, and you would be correct. Now, if you had to do some math because the numbers weren't pretty, the way you could find the amplitude is you would do 3 minus 1, the maximum minus the minimum, divide that by 2, and you would just get 1 anyway. Okay, but for this one, it's simple enough. If it's not simple enough, maximum minus minimum, divide by 2, there you have it. B stands for the frequency. Now, the frequency is found by taking 2 pi, because cos's period is 2 pi, and dividing it by the period that you have here, which is 3/4. So frequency is 2 pi over your period. My period is 3/4, so let's multiply the top and the bottom by 4/3, multiply the top and the bottom by 4/3. You cross out, you cross out, you cross out, you cross out. As tempting as it is to look at the 2 and 4 and think something crosses out, it doesn't. So I have 8 pi over 3. So B is going to be 8 pi over 3. Pretty gross, but that's what it is. C is a horizontal shift where you move left or right. Well, since I'm dealing with cosine and regular old cosine looks like this, starting up here and going down there, I have the same exact behavior. So I have no horizontal shift. So my horizontal shift is nothing. Okay, D is going to be my midline or vertical shift. Whenever you think sinusoidal stuff, think midline, and my midline is 2. So if you're thinking, oh no, let's write out the formula and circle that. Don't do that because they don't want you to write out the formula here. They just want you to figure out what A, B, C, and D are. So let's rewrite those out so they're nice and pretty. A is 1. B is 8 pi over 3. C is 0. D is 2. And that's part B. Part C has us referring to the graph in part A. Great. So I have that back. Let T sub 1 denote the T coordinate of point B. So you are also T sub 1. and t sub 2 denote the t-coordinate of c. All right, so that's t sub 2. Within the interval t sub 1, t sub 2, which of the following statements accurately describes h? H is positive and increasing. Okay, so hold on, time out. Let's break this down. Let's remember exactly what we're dealing with because it's giving me options about positive, negative, stuff like that. Remember, this is a pendulum swinging back and forth. Okay, it's up in the air in positive land. Okay, so you're 3, you're 2, you're 1. No matter what happens within this interval, so they're basically saying what's happening between here and here. Well, between here and here, no matter what, we're positive because we're above ground. This is a pendulum swinging in the real world. So we're above ground, and no matter what, it's going to be positive. Okay? Now, what else is going on here? In this case, it's decreasing because it's going down and to the right. So this is positive and decreasing, which gives us B. Pretty simple answer. Okay? Nothing crazy that we have to lose sleep over. Okay? Why they're making us do t sub 1 and t sub 2, I have no clue. Why couldn't they just stick with B and C? I have no clue. I didn't make the problem. Actually, I did. Describe the change in the rate of change of h within the interval t sub 1 and t sub 2. And if you're thinking, rate of change, let's whip this puppy out. Yes, I can do this. Let me get the numbers from the previous thing. If you're thinking that, you're doing it wrong. They are saying the change in the rate of change. What that means is if it's like you're basically saying this is concave up and decreasing. So what you're saying is the change in the rate of change is going to have me describe what decreasing on concave up means. That's what they want. Change of rate of change is something like it's increasing at a decreasing rate, or it's decreasing at a decreasing rate. Whatever going down on concave up means. Concave up means the rate of change is increasing rate. Probably terrible English there. Decreasing at an increase, or whatever at an increasing rate. Okay, so increasing rate. What this is doing is this is decreasing. So the change in the rate of change is decreasing, in other words, going down and to the right, at an increasing rate. That's the part that means concave up. So it's decreasing at an increasing rate, going down, concave up. Okay, if I were to answer this one, you would say that's increasing at a decreasing rate because it's increasing on concave down. So it all is dependent on what you're talking about. But in this case, that's that. So 3 here had 4 parts. So I would like to imagine that the way it's graded is probably dependent on you showing work or you explaining or the fact that we had to do 5 points on the one part. But yeah, that's 3. So that's free response question number 3. No calculators, lots of science stuff. Expect to see something like that. Like I said, in almost every single free response practice problem, I ran into this picture right here. Almost every single one, you run into this picture. Does that mean you're going to run into the same exact problem? No, but I would bet some money that you're going to be given some type of oscillating thing that maybe goes around in a circle or goes back and forth, and you can answer questions that we just saw. So be ready for something like that. Okay? That was fun. Hope this helps. Okay, don't adjust your YouTube, okay? This is free response question number 4. Before you do free response question number 4, they're going to give you a set of rules. The first 2 are kind of obvious. Assume things are real numbers, check. Trig stuff is measured in radians, check. Now, the third one is you will be given things that should be simplifiable. If you can simplify them, simplify them. For example, log base 2 of 8 can be written as log base 2 to the third. base 2 cancels out, you get 3. You should be able to do that. Don't leave that like that. Cosine of pi over 2 is the x value of pi over 2, which is 0. You can simplify that. And the inverse sine of root 2 over 2 is the y value where you get root 2 over 2, which is pi over 4 and 3 pi over 4. So you can do those, guys. Don't leave your answers looking like that if you can keep going. All right. The fourth bullet says you can simplify these guys too. Like, don't be stupid and say, oh no, let's leave it as 2x and 3x. Oh no, let's not change it into that. Oh no, let's not change it into that. Oh no, let's not take the fact that if we add ln's, we multiply the inside. Simplify them if you can. Now, if you're not allowed to use a calculator. So obviously, you're not going to be expected to know what ln of 15 is, but you are going to be expected to combine things, add the exponents, subtract the exponents, combine like terms whenever you can. And for each part, show your work. There we are. So here we are. We're going to be given a bunch of algebraic situations that we're going to have to answer based off of the things that we're given. Okay, so this is part A, 1 and 2. We are given f of x. We're given g of x. 1 asks us to solve x if f of x is 6. So I'm going to take this guy right here, and I'm going to set 6 equal to ln of 9x squared. Now, first things first, I have ln all by itself with some stuff in the middle. I always like to take the e to the of both sides. I know it's not the grammatically most correct thing in the world, like that sentence I just said was, but that's what I like to do. If you would rather just write it out in exponential form, fine. It's the same thing. E to the ln of x is 9x squared, and you end up with e to the 6. Don't get your calculator out. You're not allowed to use one. I need to get x all by itself. Divide by 9, divide by 9. That crosses out. So you have e to the 6 over 9 equals x squared. Now, in order to get x all by itself, you have to square root both sides, and do not forget your positive or negative. Okay. Now, before you're like, I can't do anything. Sure you can. You can do two things, and let me write it over here because I'm out of space. You could do two things. The square root of e to the 6 is asking what times itself is e to the 6th? E to the 3rd. Easily, what times itself is 9? 3. And you have plus or minus e to the 3rd over 3 equals x. Wait a minute. Can I take this guy and plug it into that guy and have it work out? Usually when I have negatives and ln's and stuff like that, I'm not allowed to do it. Well, I have news for you. You are allowed to plug in the negative, because before you take the ln, you plug in negative something and then square it, which makes it positive. So my answer is both positive or negative e cubed over 3. Now, obviously, we don't have a calculator. You can't simplify that. You can't do anything else with that. That is going to be our guy, and that's what we're sticking with. Okay, so kind of a tricky problem, but, you know, we did it, and I'm proud of us. Okay, part 2 of part A has me setting this guy, which I know it's kind of faded, but you have 4 to the x plus 1 over 4 to the 5th equals, what was it, 16? Now I know what 16 is. 16 is 4 squared. And while I'm at it, why don't I multiply both sides by 4 to the 5th? Why don't I multiply both sides by 4 to the 5th? So I have 4 to the 5th times 4 squared equals 4 to the x plus 1. Just like we saw on this slide that told us all the rules that we were supposed to use, whenever you multiply terms of the same base, you add the exponents. And if you're like, what do I do? Should I get logs? Nope. If you have 4 to the stuff equals 4 to the stuff, set the stuffs equal to each other. So 4 to the 7 equals 4 to the x plus 1 means 7 equals x plus 1. Because you would log base 4 both sides, make the 4's go away, and this would just happen anyway. Subtract 1, x is going to equal 6. There's no rules here saying that I can't do this. And Yeah, this kind of makes sense. I mean, if you were to go up here and say 6 plus 1 is 7, so 4 to the 7th over 4 to the 5th equals 4 squared, which is 16, which is what I'm supposed to get. Check, check, checkaroo. Now, checking this is not going to be near as friendly, but you could, if you wanted to, just trust me on that one. I did it right. Just trust me, please. I did it right. All 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 right, so what we have is h of x equals 6 log base 3 x plus 1, 4 log base 3 y plus 1, minus log base 3 z minus 4, and j of x is some trig-looking thing. One says express h as a single logarithm. Ooh, I like these. Whenever you're adding and subtracting logs of the same base, which, by the way, we are, step one that you always want to do is deal with the coefficients. If you have a coefficient, you can simplify that by making it an exponent. So you become log base 3 x plus 1 to the 6th power plus log base 3 y plus 1 to the 4th power, and nothing happens with u, minus log base 3 z minus 4. Then what you would want to do is organize all the pluses together and all the minuses together, and that's already taken care of. Step number 2 is if you add logs of the same base, multiply the inside. So this becomes log base 3. I'm going to put a nice little bracket here. X plus 1 to the 6th times y plus 1 to the 4th. We're going to leave it like that because I can't imagine we're going to be expected to FOIL this out 6 times, that out 4 times, then do a train wreck of a problem. I think we're okay leaving it like that. You're still going to subtract log base 3 z minus 4. Now, when you subtract logs of the same base, you divide the insides. So last but not least, our single logarithm is going to be log base 3, x plus 1 to the 6th, y plus 1 to the 4th didn't change. That's going to be over z minus 4 in an unnecessary parentheses. But now we have everything in a single logarithm. Hooray! I love it. I love it. And that's I. Double I is going to have me express this as a single trigonometric function. All right, whenever you're dealing with things that involve sine, cosine, secant, tangent, cotangent, cosine, you're going to want to change every non-sine cosine thing into its sine cosine version. So sine doesn't change. We still have 1 over sine x. Cotangent, however, is cosine x over sine x. Okay, so if I were to make believe that that's over 1, I know that that simplifies. So that leaves me with 1 over cosine x. Now, if you're thinking, that seems good enough to me, that is a single logarithmic function. Yeah, well, that 1 up in the numerator upsets me so. So remember, 1 over cos x is the same as secant x. So that's going to be our guy there. Just like that was our guy there. I love these. Oh, I love them so much. I love the algebra versions of these things. It just fills me with glee. This, on the other hand, is probably not going to fill me with glee. But we'll see what happens. Like k of x equals 6, the inverse cosine of x root 3, and m equals 3 inverse sine of root 3 over 2. Find the value of x in the domain of k that makes k of x equal m of x true. So I got to set these puppies equal to each other. Gross, 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 gross. All right, so I've got 6 inverse cosine, x root 3 is equal to 3 inverse sine of root 3 over 2. Okay. I could divide everything by 3 if I wanted to. Might be helpful. I don't know. Maybe, maybe not. So that gives me 6 cos inverse sine of x root 3. That equals the inverse sine of root 3 over 2. Now, I know what the inverse sine of root 3 over 2 is. The inverse sine of root 3 over 2 is the y value on the unit circle. That gives me root 3 over 2, and that is pi over 3. So you become pi over 3. Okay? So I now have 2 cosine inverse x root 3 of both sides. I can divide both sides by 2, which kind of seems counterproductive. By the way, that's the same thing as multiplying by a half. So again, kind of seems counterproductive to what I did before. But now I have the inverse cosine of x root 3 equals x, or pi rather, over 6. Now, I need to somehow unlock that x. Now that I have all this cos stuff all by itself, I need to get rid of that inverse cosine. Well, just like we would use inverse cosine to get rid of cosine, I could use cosine to get rid of inverse cosine. It works the same way backwards. Okay, so you cross out, and we're left with x times the square root of 3 equals the cosine of pi over 6. I know what the cosine of pi over 6 is. The cosine of pi over 6 is root 3 over 2. I can divide both sides by root 3. So divide both sides by root 3. Okay, which, by the way, is the same thing as multiplying both sides by 1 over root 3. These cross out, and you get a half. X equals a half. So was this part fun? No, absolutely no. And this, again, is one of those things where the kids who get 5s will get that right. So great. You're not expected to get every single problem on an AP exam correct. So if you get to this point at the very, very, very end of the test after 4 multiple choice problems and 4 free response questions, and you're losing your mind and you're going insane, and if you look at that and you're like, nah, I don't blame you. But you can do it. Put your mind into it. This concludes the ultimate GOAT AP Precalculus Practice Test version 1.0. I'll probably make a 2.0, but this is the first one, so thanks for watching, and as always, I hope this helps.